So, hello everyone. Um, I guess the string is working. As I get some feedback on my phone that it should be live, and I see the video as it should be playing. So, yeah, I guess everything is ready to start. So, yeah, today, after the last stream I made, which was quite a long one, which I hope won't be the case this time. Where I talked about how to create a setup for the Porsche Cup at Daytona. One viewer sent me a message afterwards, and he asked me to talk about aerodynamics and how we analyze aerodynamics in a race car, and how we can use data analysis software to improve our performance on the track. So that's what I'm gonna talk about today. So yeah. Um, Before I start talking about, yeah, David, I can see your comment. You can see the live chat normally as well. So I guess everything is fine. So before I start showing you data and some other things, I think I should make a small introduction to what race car aerodynamics look like in a larger scope. So I found this nice slide. It was actually the third result on Google when you type race car aerodynamics. I can type the link in the description afterwards. So this one is it covers a lot of things, and it's way more technical than I actually want to get in this video. But you can see there is plenty of information on how a car creates downforce and what do you use, what kind of formats you want to have in the car. But that's not what I want to talk about. There's plenty of better info if you want to learn how you generate downforce, how you generate drag in a race car. I want to talk about how we're actually going to use it to our favor. So how we actually arrive in a racetrack and I say, oh, what kind of wings are we going to run, or what kind of ride heights we're going to run. Most of the times, we already get an aero map from the manufacturer, and that's generated usually in a wind tunnel. And if they have loads of money, they're gonna go in a racetrack and try to measure it without a wind tunnel. And but usually it's a validation process because the wind tunnel is really quick, and even if you have loads of money to do infinite track testing, it doesn't make any sense to only try this in wind tunnel environment. So what does that all that testing gives us in the end? It gives something like this. This arrow map isn't very explaining and very we say I don't know the word for it in English. In Portuguese we say didactic, but I don't know if that's even a word in English. But it's easy to see. There are easier ways to show information. But basically, what what it shows is here describes the magnitude of the aero loads as a function of the ride height. So it's gonna say, let's say your car is running 20 millimeters above the ground at the front, and at the rear it's running 30 millimeters above the ground. That ride height is going to give your car, considering it has the same set of wings, but let's keep it simple for now, it's going to give an X amount of downforce and an X amount of drag. And that's what these level curves are showing you in a very complicated way. It doesn't have to be like that. There are better ways to show that. And how can we measure this on a racetrack? So first we have suspension sensors, which for most categories except, let's say, LMP1 on LMP2 and Formula 1 are not allowed. So suspension measuring for most of the time, most of the racing categories around the world is not allowed. Um, More often you can find laser sensors measuring ride heights, and that's a really good way to measure it, unless you bottom out and the laser sensor will be gone. But that's a part of racing. And why that's good? Because you don't have to take into account tire deformation or estimate tire deformation, which can be a really hard thing to do, especially as tires change pressures pretty much all the time. And then you can do some coast down tests, but that's more like to the project and the design phase of the car, not like let's apply this to the track. You can also play some strain gauges, which are gonna measure exactly how much force is being applied to the suspension, so you don't have to calculate it using springs, how much force the aero loads are actually producing in the car. So that's even better if you have a strain gauge to measure it. As well, you can look at air speeds, but for simulators, I don't see much use in that because winds don't change as often, and we use this to measure if there is a tailwind or a counter wind, and that changes the aero loads. Especially, I was in a race in Estoril in the middle of this year, and we had winds of up to 70 kilometers per hour. So when the wind stopped for a brief time of a brief period of time over the weekends, the top speeds increased by quite a lot. So if you have really strong winds, you also have to take that into account. And let's say the wind changes direction, so you have to use a completely different downforce setup than you were using, because you're not gonna have the same amount of downforce in a specific corner as you had some days before. So you have to also think about winds in real life. So here, there is a very good article in Racecar Engineering website explaining what is an aero map, and here there is another way to represent that. So the red dots, the red part of the map is where there is the most downforce being generated, and you can see the red having the most drag being generated here. So yeah, you basically have loads of way to represent it. The way I like the most is the one that you put in the software, so it's gonna give you the values depending on what you use in your car. And you can do that in the simulator by going out in a straight line and testing it yourself in a track like Le Mans, for example. But usually I don't have the time to do that, and I don't do this kind of testing unless I want to take each and every 10th out of my lap time, and then maybe you can find an operating window which everyone is not running, and you're gonna be the first one to run it, and I suggest you hiding it until race day, because it's very easy to find if you're not on that operating window, because as you're gonna see later, you can easily check that with speeds. So this is what an aero map looks like, the way I like to see it. I think that's the easiest way to interpret an aero map. So yeah, here you see the way I like the most. So yeah, as you saw, there are many ways you can have an aero map, and usually the manufacturer is going to give you that already, so you don't have to do all the guesswork by yourself. And sometimes you don't want to trust the manufacturer as well, so you try to do your own testing. But we're racing can be as complicated as you want it to be. So yeah, you pick your choice into what you think is gonna make you faster, and what you need to be faster. And but then, how do wings influence the car? So I picked up this data. It was generated in R Factor 2, which is a game where I found out that changing ride heights for most of the cars don't have that much of an effect on changing the downforce of the car. So this is the McLaren Senna. It's you can see it's Nürburgring GP, and here I have three different rear wing configurations. Don't look at the lap times because they are really close. I was more looking into making a car comfortable to drive using different wing configurations, and that car generates a lot of downforce even at lower speeds. So it has a big difference pretty much for the whole track, especially for the fast turns, like let's say the Schumacher S, which is really high speed. You see over 200 kilometers per hour. So in those corners, you really want to pay attention into your aero balance, which I'm gonna talk later. So if you want to see first how I personally set up my workbooks in Motec to see aero. So here are my math channels. Most of those are not of interest right now because they don't talk about Aero. But in Aero, I'm gonna link forum post I made where I explain this in text, so you can have a look later into how I calculate those things. But here are my expressions that I use to calculate downforce. So here, I pick up this instant weight front is a channel which sums up the loads of the front suspension. Our Factor 2 already gives that out to you without a function of the spring compression, which I have to do in iRacing, but not in our Factor 2. So that's already most of the work being done. So here, I take that instant weight, and then this is a more simple expression. You're gonna find my iRacing workbook is a little bit more uh, elaborate than that. So I pick up the instant weight at the front, and I subtract to what would be at the front of the car under a static load. So that's a simple way of measuring it. And there is another way of measuring it, which is the front downforce 3 channel, which is the more complicated way. I already introduced it, that didn't remember that, that I had already introduced it. So here what I'm doing is basically the same thing, but I'm taking into account the load transfer generated by the fact that the car is accelerating in a longitudinal direction. So I'm pressing the throttle or pressing the brakes. So this uh, a more complicated expression is just to compensate for the load transfer under those circumstances, and it doesn't make much difference in, let's say, when you go in a straight line where you can easily compare the downforce values and the drag values and stuff like that. But it does make a difference under braking and accelerating, so you need to take into account that load transfer. So yeah, this is what I use to calculate this. And here, as our Factor 2 already gives that out to you, the suspension loads, you don't need the spring rates of the car and the motion ratios of the car to have the exact downforce value. But if you are talking about, let's say, I'm gonna go to my iRacing workbook where I'm measuring in the Porsche 911 Cup. I need to have my spring rates, and you may look at this value if you have seen some spring rates and think it's a little bit low. That's because iRacing, uh, it basically the Porsche 911 has a helper spring which helps the springs to keep seated in case it extends. Let's say you go over a curb, the car is in the air, so just so the spring doesn't fly out of the car because it's not being compressed, so it's basically free to go out of the car. It has a helper spring, and that acts as a spring series. But as soon as it's completely compressed with the car load, it shouldn't have an effect. But iRacing takes that it's working as a series throughout the whole suspension travel. So basically, the car has a softer spring than it should have if it was correctly simulating the real-life behavior. But to get the downforce values making sense, I noted that, and but that's fine. I guess that's an approximation they wanted to take, and I think they had way more data than I have to compare the real car to the simulated car. So I'm not gonna talk about this physics issue now, but you need to have a great approximation of the real spring rate of the car. Usually it's showing a setup screen. But if, let's say, it's giving much higher downforce, because in this case it was like the static load of the car with no downforce, it was saying the car was weighing 3,000 kilos, and that's absurd for a 911 Cup. So that's how I found that out. But there are plenty of ways um, to see what spring rates you're running. You can use the formula for a spring, which is spring force. Let's go to Google. So yeah, the Hooke's law, which is the force of the spring will be equal to its movement times the coefficient of the spring. So that coefficient of the spring is what you want to put in that calculation. So really basic formula, and you can find that out using the suspension travel channel and what you would expect from the suspension loads. So Now I'm gonna show you. I showed you how I use these downforce channels, and then there is another channel which is important to mention, which is the aero balance channel, which takes that front and rear downforce and basically divides it one over the other to see how much downforce you have at the front of the car and how much downforce you're generating at the rear of the car. In this case, it's generating 40% of the downforce at the front of the car for this data set I'm showing you. So now, talking about rear wings, oh yeah, and there is the rake channel as well, which I use to compare. Let's say I made a ride height change and I changed the tire pressures as well, and then I changed the camber, which changes the tire spring rate, so it's gonna affect dynamic ride heights. So what I want to do for rake is have a quick way to look at how much the car is a wing by itself, because if it has, let's say, if it's inclined, and think of Nürburgring, like if you are to move this thing into the air, it has about a 45-degree angle in this drawing. So you expect it to go down. Just think about your hand when you put it out of the car. So if you change your hand inclination relative to your direction of travel, you're going to see that you can generate downforce by changing that angle, and you can generate lift by, let's say, moving your hand upwards. So that's a quick way to compare things. When I look, oh, the rake got closer to zero, so I'm expecting it to generate less downforce at the front, so less downforce at the rear as well. I'm expecting it to have less drag because it's basically an arrow traveling through the air. And yeah, that's the main channels I use. And also, I highly recommend when you're looking at any kind of aero data that you put some kind of speed channel to compare the data. Because let's say I'm gonna look at this lap where I was massively slower. So let's look at here. So I'm about 10 kilometers per hour slower, and if I didn't have that speed graph and I was saying, oh, there's a problem with the car because it's generating much less downforce than it was before, but it's not a problem with the car at all because it's just slower, so it's gonna move less air and generate less downforce as a consequence. So yeah, I highly recommend having that in when you're looking at any kind of aero data. So now, what I wanted to show you in this data is the difference between having different rear wings. So I think here I started with a higher angle of rear wing, and here it was less rear wing. And yes, that's right, because you can see that the front downforce doesn't change much. See how the red line is really close to the white line, which is the one I removed with the rear wing. And if you look at the rear downforce channel, you can see that there is less rear downforce, so the car is generating less overall downforce, as you can see in this channel. Not that much, but it is. But look at how much the aero balance changes. So it's generating much more of the downforce at the front of the car than it was before. And why is that? Because at the same time, you can look at the rake of the car also change it by quite a lot. You increase the rake of the car, and the whole car is acting as a wing. And the more rake you have, generally, you're gonna expect to have more front-end downforce of the car. So that's why the aero balance shifted that much forward. And that helped. I remember driving that car, and that helped it a lot. And you can see that the lap time, here it was about the same. But then I say, oh, I think the car is okay. I think that lap was a mistake. So I went, and in this data, you can see that I came back and checked it again. So to see, oh, I'm gonna come back to another. I think I changed the ride heights here as well. Yeah, I did, because the rake is different. So here, what I did is I increased the overall downforce level of the car, having less rear wing, and the aero balance comparing to the start was about the same. So I noticed that I needed more downforce at the front, so probably the car was a little bit oversteery but I saw an indication that it was getting better over time. So that's what I wanted to do, like find a compromise, and you can see the lap time it improved by a little bit. So yeah, that's how I usually analyze this. And here I analyze drag. I can compare. It's generated by Motec automatically, so it compares accelerations from a certain speeds to another certain speeds with the different setups used. So that's a good way to measure how much drag you have in the car, because it's gonna basically affect your straight line speed and accelerations. And here is really good place to look at statistics. So it already takes out the average of aero balance throughout the whole lap. So I can easily compare two setups, just looking at this table and say, oh, I think the car has more front end aero. So I just come here and say, yeah, that's my perception was right when driving the car. So yeah, this is a great way to have a quick look at your data, and you usually to have a drag channel in R Factor 2, but there is no downforce channel anymore, a drag channel anymore, which is completely realistic as well. So I'm not complaining that much. So yeah, that's how I look at it, and so basically it's just about driving your car and saying, oh, at high speed corners, do I feel like I'm spinning out with the rear, I'm oversteering, so I need to add more drag. And how do you do that? You either reduce the rake, so you generate less drag at the front, or you increase the rear wing. So those are two ways of doing that. Vinícius, se puder deixar no... So yeah, sorry for the little pause. I had to mute a video that started playing over on the other side of the room. So yeah, that's how I look at the data when I'm doing a setup for the car. And here is another example where in a car that the ride heights have a really huge effect in how you run the car. So this is the Porsche 911 Cup in iRacing, and the green graph is running 130 millimeters of ride height at the rear, static measurement. So this is quite interesting, because you did expect that you were gonna generate a lot of downforce, because the car is basically a big wing with loads of rake. It has like I think it's 50 millimeters of rake of the car when it's static, and when driving it was getting like way above that. It was getting like still 40 millimeters. So you can see you would expect it to generate lots of downforce, but that's not what happens here. You see that rear downforce drops by quite a lot. I'm just gonna show compare like the two. So you see like it even generates lift from the rear. So but the wing is sitting higher, and you have like basically the same wing angle. How does it generate lift? I don't know, but the data is showing that. And if you compare the aero balance, you can see that you have a lot more at the front, and you can see the aero stats showing you the same thing, because you see the shift um, of aero balance to the rear when you change the ride heights. And if you go like, if you compare those two laps, you can see that it's very oversteery in the data where the car didn't have any rear downforce, especially at the braking zones. So the car doesn't generate much downforce, so that's why you don't see a huge difference. But you can see that, look at the steering wheel angle of the white lines. Look at how I can use much less steering wheel angle, and it vibrates a lot. So that's that's an indication of severe oversteer with the car. And look at those are the same wings being used. I didn't change the wing between all these data sets. So here it was a middle ground. It was 115 millimeters at the rear, and the red is at 100. So you can see that it started to generate rear downforce, but you know, say, oh, the car is a lot better. I think it's driving better. I'm feeling more comfortable with the car, even though the lap time was a little bit slower. But there was a difference in tach temperature here. So, and I didn't wait until the tire warmed up properly. And in the other setup, which is the one I put 100 millimeters, you see that it has the same downforce. But when I look at the speed graph, you can see that the red graph, okay, there is a little bit of better driving, but if you go uh, scrolling through the laps, you can see that the red has a slight advantage in top speed. And why is that? Because it has less rake, so uh, it has a smaller frontal area, which generates less drag. So if I'm generating the same amount of downforce, I want to run less rake, and that was helping the car as well, because I was feeling it was a little bit oversteery, and lowering the rear ride height also helped with low speed corners in that regard. So, so yeah, that's basically how I look at aero in simulator data, and that's providing you have a suspension sensor or a strain gauge to measure the loads. So that's not always the case. Sometimes you don't have that, and you're just gonna have to rely on your own feedback or the feedback of the driver you're working with. And sometimes they don't know how to tell the difference. And basically, you want to look at high-speed corners, and I'm talking about going above like 150 and 160 to generate some kind of downforce. Um, there you want to worry about aero, and increasingly more as you, let's say, you have a 200 kilometers per hour corner, you want to worry about aero even more there. So, so yeah, if it's a high-speed corner, you should look at tuning your aero. And if it is a low-speed corner, you aero won't make that big of a difference unless you're driving, let's say, a Formula One car where a low-speed corner isn't that low speed at all, unless you're talking about the Monaco hairpin. Um, so yeah, that's basically how I look at aero. If you have any other questions regarding this, just type that in the comment section, and let me know what kind of video you want next. And yeah, I think that's it for today. Oh yeah, one last thing that I want to emphasize is when you're making a change to the car, let's say, oh, I'm gonna have the perfect aero of the car. Don't forget about the other aspects of the car, because if you change one thing on a race car, you're gonna change another thing as well. Because changing ride heights changes load transfer, and load transfer dictates a lot in the behavior of the car. Changing tire pressure is gonna change your aero, so yeah, think about be wise when making changes, and try to minimize your changes as much as possible. So don't go changing a lot of things at the same time, and try to not make big steps in adjustments, so you are likely to fall into a deeper hole than you already are, because you're not gonna find the operating window of the car. And last tip that I remember now is, if you're having a way different top speed than all the other cars, and you were being slower, and probably going to be a lot slower than other cars, you're probably on the wrong aero operating window. So just throw all your aero settings in the bin and start from scratch, because you need to be at roughly the same top speeds, unless you have a big engine difference, which usually isn't the case in sim racing. And but yeah, that's it for today. If you have, as I said, if you have any other questions, just let me know. And yeah, that's it for today.